Ken made the observation, he's right. We're taking the chapters out of order. We did 1, 2, 3, jump to 6. 4 and 5 are in the middle. It says, Network Guide 4th Edition, Technologies and Access Methods. Read that layer 2. What we try to do, jumping around the chapters, is stay pseudo, I said pseudo, and pseudo is probably a good word, pseudo consistent with the OSI model. Try to keep these things in that kind of perspective. The OSI model, again, the thing that everybody loves to hate, something that is important when you particularly do troubleshooting, and how much of it's involved in the OSI model. Honestly, when we looked at that thing last time, when we got up the application layer, not a whole lot took place in the wiring itself, did it? I'm going to pick on Tom because he did the top 3 layers. A lot of that happens kind of on the machine itself. The rest of what we do are going to happen up through routers when we're transferring the information from one location to the other. And hopefully after you look at this thing, what we do is take a little bit of information and build a huge packet in it, encapsulation. Each layer gets its own information. So we build this huge packet around encapsulation and decapsulation in order to get a little bit of information delivered to a specific machine. If you're going to yahoo.com, you really like to get to Yahoo's web server. If you're going to Moodle, you really like to get to the Moodle server. And you'd like for the answer to come back to you, right? That's always helpful, too. So that's what all of this encapsulation is about. To get it there, the little bit of information, send me this web page. And when you look at what's actually in the data, kind of sometimes it's disappointing. I think one of the things that really is impressive, at least to me, is when you start a protocol analyzer, sniffer, whatever you want to call it, and see how much traffic's actually out there, just on the wire. Particularly in a Microsoft network. Microsoft is really a pretty chatty operating system. So there's lots of information out there with it. The objectives of this one: describe the basic and hybrid LAN physical topologies, their uses, advantages, and disadvantages. When we get into topologies, and hopefully become a little bit clearer as we go through those things, we've got 2 types of topology. We've got a physical topology and a logical topology. The logical topology, electrical topology. The two terms that we'll look at them in a little bit more detail in this chapter are going to be the ones we're concerned about right now are ring and bus. Are there others? Yes. There's a whole bunch of them. The 802.1, the 802.x, 802.3, 802.5, 802.11, 802.10, and on and on and on. All of those define a logical topology. The one we're going to talk about is token ring, token passing, and bus. And bus is going to be one we're going to call, and we'll get into it. Don't worry about the letters right now. CSMA-CD, we have a CSMA-CA, we have a token ring, we have a token bus. They go on and on and on to the different types of topologies. We have one called polling, where a central machine, and when I was in the Navy, that's exactly what we used to transfer our data at sea from ship to ship. There was a central server, a central data processing ship that went and polled, asked each ship if it had new data or to send its data, so it sent its contact data. That way you can build a much larger field of contacts, interest, enemy, whatever you want to call it, when we go through those things. Yes, they still use it that way. And now the ones that are the central units are like AWACS, Aegis ships, because they've got so much more processing power and the capability to handle so many more targets. But yeah, but if I'm sitting out there on my little old destroyer, with not a whole lot of armament, I really like to know when the bad guys are coming. And they send that information polling. And that's the only real logical way to do it. In a situation like that, when we go through these things, how else are we going to do it without causing interference, and that's the only logical way that they've come up with it. Yes, they still use that. And does it change that rapidly? Yeah, I guess if you're being attacked by air contacts, yes, but otherwise, no. And you can put, in the polling, you can put one ship in more frequently. For instance, you could put the Aegis ship in, to be twice as frequent a transmitter or responder as you did anybody else, or 3 times, or whatever else you wanted to do with these things. Backbone structures that form the foundation of most LANs. Backbones, term here, what a backbone is something that connects networks together, basically. Backbone, high speed. If we had a bunch of servers in an area like this, not a big backbone, but we would have a high-speed segment. The Internet has a backbone. We'd have a high-speed segment, and then we would have our lower-speed segments in here. We kind of sort of have that in a corrupted sense, in that each of the rooms has a gigabit connection to the NOC. Goes to a gigabit port over there on a gigabit switch, a gigabit layer 3 switch. We'll get into some of those terminologies later. And inside the room, we use 100 megabits per second to go to each of those machines. Is that fast by some of today's standards? No. Is that fast by older standards? Yes. Because now you're talking 10 gigabit and gigabit NICs to the machines themselves. So what is a backbone? A backbone really is just a high-speed connection. And we'll look at some of those. I think collapsed backbone is what they call ours. The different types of switching used in data transmission. We'll go through those. It's important to understand the terminology, but honestly, with the development of the hardware, it's important to know that those types of switching exist, but mostly they're not used anymore because of the hardware stuff. Transmission methods, underlying Ethernet, token ring, FDDI, and ATM networks. FDDI is fiber. It's an old standard, really not used a whole lot anymore. What it is a ring, counter-rotating ring with fiber. And ATM is not the place where you get money. It's asynchronous transfer mode. This is one that kind of is used, mostly what is used in this, an ATM would be a wide area network protocol. Mostly what's used there is frame relay, and that's the one that you'll learn how to configure in the Cisco course, be the frame relay. FDDI, yeah, token ring, not really all that popular. One of the reasons not really all that popular is proprietary to IBM. Ethernet is probably the most popular because it's really easy to add a computer to an Ethernet. I mean, if you add a machine to an Ethernet, the only thing you got to do is plug it in. Except in this room, because I have port security configured on the switches, and if you plug in the wrong machine to the wrong port, it just goes away. They kind of got, or I kind of got, Chris, I told you it's my job to keep him busy, but they had a course, I don't know, a couple months ago, I guess, in this room, and they had to bring some machines out of room 109. And when he put them back into 109, didn't remember exactly where they went, plugged them in, shut down a bunch of the ports. Didn't matter that they had been there, they were now plugged into the wrong port. So when we talk about these things, and where this is layer 2, that's a layer 2 function, to be able to control that. Try to work some of these things in, we talked about it a little bit. Anything in the security world that I can control at a lower level of the OSI model, for instance, physical control. If I can keep people from actually getting to the stuff, I don't have to worry about anything else. If I can control it at layer 3, I don't have to worry about the higher layers. If I can't control it at layer 2, I don't have to worry about 3 and 4. If I can't control it there, then I try to do it at 3 and then try to do it at 4. We do get in the application layer controls there. We'll talk about in the security classes application layer firewalls and things like that. Firewalls, how you configure a firewall. Most firewalls, the firewalls that we think about are going to be layer 3 and 4 devices. Application layer firewall, layer 7 device. So we'll try to get all these things worked into. The OSI model, is it a big deal? Yeah, kind of. Characteristics of different wireless network topologies, including Bluetooth and the 802.11 standards. This one's a little old. They didn't really talk about, I think they kind of talk about N, didn't really talk a whole lot about N. And now the 802.11ac. Has anybody looked at that standard? We're talking gigabit speeds on wireless. 802.11n is supposed to go up to something like 750 meg, theoretically a gig, I guess. But 802.11ac, which is in beta, you can buy devices. They're not cheap, but you can buy 802.11ac devices. And they're talking gigabit, up to gigabit speeds wirelessly, which is a pretty big deal. Because we've been fooling around with, what, not real fast at all, wireless for years, and now there's a breakthrough in these things. So, yeah, it's a little interest there. Find anything good on it?
There's a bigger breakthrough than that. There's American and Israeli researchers. It's called a twisted vortex beam.
Yes. Yeah.
2.5 terabits per
Yeah.
second.
Yeah.
Only within a meter.
Yep. Yep. And what?
Only within about a meter.
Only within about a meter. Yeah. So that'll work great for my Bluetooth device, right?
Well, I mean, what in the world would you put a terabyte over a Bluetooth?
Math is
The way these things, and why would you do that? The way these things start, they don't start going very far. They really don't. That's going to be a while. Yeah, the twisted vortex is there. 802.11ac is something that is real, that's on the horizon, that you can go more than 1.5 meters or 3 meters or whatever. Is it going to go better and better and better? Yeah, and there are other wirelesses. There's a wireless internet provider right here, right? Yep. Oh, I knew you were going to ask that question. The name's not coming to me. It will at the most inconvenient time in a little bit. But when I was at Blue Ridge Behavioral, we had that a lot of the different places because cable wasn't available at some of the sites that we used.
It starts with an H. I know you're talking about now.
So they are there, and reasonable speeds with these things. So wireless is something, and wireless is an area that the Network Plus has started to focus more on. Because honestly, before these newer standards and the newer security, what did you use wireless for? Home networks, and hope it wasn't anything useful enough for somebody to try to crack, try to hack. Yeah, not WPA or WEP, WEP not very secure. WPA much better. WPA2 is really a good protocol. Are they crackable? Yes. Is anything uncrackable? No. Why do you change your password? Because the reason that we force password changes is if somebody gets the password, gets the encrypted password, that it is strong enough to take enough time that by the time they get it cracked, you will have changed it. People get these individual keys, session keys. How long is that good for? It's good for that session. Once you hang up, once you close the browser, that session key should be destroyed. So those things, all different parts of what we do, will do, should do in networking. Physical topology is what it looks like. In a bus, just like a bus line, a bus is everything's connected to a single piece of wire. A ring goes around in a circle. Everything is connected from one to the other. A star, a physical star, everything goes to one physical location. And that's about it as far as physical topologies, isn't it? And can you think of others? I mean, wireless is going to be a star physically, honestly. So physical topology, what it actually looks like. When we talk about the physical layout of the nodes on the network, 3 fundamental shapes: a bus, ring, and a star. When we talk about those, bus and ring can be both a physical and a logical topology. Physical topology, the way it looks. Logical topology, the way the electrons flow. A star is only a physical topology. There's no logic about it. And I've done this before. See, I got to use my little pens here if I can make it work. The last time I tried this, it made things really big. On a bus, if we take the bus and we connect our, I'm not even going to, yeah, I will too. Draw our highly sophisticated computers on it. Each of these things, and there is I'm just going to draw a circle here, terminator at each end of a bus topology. There has to be. Are you going to see these things? I doubt it. That's something that when we moved into this building in '97, we had a true bus, a coax bus. What was really neat is the room where the library is now, we used to have, 50, 60 computers in there, so we had different segments for them in case something went down, because on a bus here, if anything goes down, the whole thing goes down. And students used to love to come in and, undo the T's and make them look like they were still connected. And then you got to troubleshoot it. Well, what you do is find out where it is. You go right to the middle. If you ever have to troubleshoot one of these things, anybody ever had one of these wireless dog fences? What happens when it goes down? It's just a piece of wire. One piece of wire goes around in a circle. What happens when it goes down? What do? Go right to the middle. And it'll be okay on one end and not okay on the other end. Go to the middle again on the bad side. See which end works. And keep having it. Do the same thing on a bus. If I have a problem, nothing's working, go to the middle of the bus, put a terminator on each end, which part of it works. And then go to the middle again. And then you can troubleshoot it relatively quickly. But anyhow,
I still haven't figured that out, because when you have that thing wrapped around, when you're running it back to your primary power supply, and
right,
but you twist it.
Only if you don't want the signal. Hey, that talks about twisted pair, and that's exactly right.
Yeah,
on these things, if you don't want it, like you want to have an area where your dog can go and it doesn't trigger the collar, you twist these things together, right?
Right.
You don't have a signal. Hey, reminds you of twisted pair? What if we don't want our...
What is happening?
What's happening is...
Is it doing like black noise? Or?
What's happening is, if we have signals here... Boy, I'm making a mess today, aren't I? Electrical signals, okay? And we have phase. We talked about phase, didn't we?
Right.
What if I had these two signals, one, if they're together... and they're close together, what's going to happen?
They're still going to run...
They're going to get bigger.
Right.
Why? Because they're in phase. What if I shifted these things so that instead of... I just draw another one here. Let's use a different color for our other one, our out of phase one. How's that? What if I did that?
So you are basically creating...
When I have creating a cancellation.
Black noise.
Black noise is a different kind of thing.
Well,
You're talking about the noise suppression, yeah. But what we're doing this is electrical. That's why I don't want to do noise.
Yeah.
But if I have a +1 and a -1, plus a -1 equals 0, so I get a cancellation. That's what the twisted pairs do for you. Because you twist them, you actually shift these wires a little bit. And what's the issue is when we do things, run them across through noise, and you don't want to run through noisy areas, that you get the noise on these things and they're in phase with each other, they're going to become much bigger. This one, if we did these things, then we would have one really large signal. But the twisted pair, the physical twisting, and I don't think we really go through the categories. There's cat 1, 2, 3, 4, 5, and 6, and going on and on and on and on. What's the difference is how many twists, basically, are in the wire. Gives you the noise suppression. Because when we go from a cat 3, 10 megabit per second wire, to a cat 5, 100 megabit, and cat 5 goes a gigabit, right?
Yeah.
What actually changed? We still got 4 pair of wire. They're still twisted. They're still the same gauge. They still use the same connectors. What's different is the number of twists, the noise suppression, basically, that goes on in these things. So it takes more wire, obviously, with the more twists, but those things. Now, when you get into the higher ones, yeah, they have some other things. They are a little bit thicker, and they're much more of a pain to work with. A cat 6 is.
They put more juice through the 5s and the 6. Is that why you need more twists?
Say again?
They put more juice through cat 5.
Yeah, and as we go through up to higher speeds, they're using more of the wires. You ever wonder why they only use 4 wires? The way this thing was designed was 4 wires were supposed to be for the data, and the other 4 wires were supposed to be for the voice. But it never really worked out that way. So and now they're getting into the higher speeds. They're actually using all 8 wires in some of those.
I noticed there's a whole of unused.
They're just there. I said initially the design was supposed to be, you're supposed to have one plate that went into a workstation, and supposed to have one plug for voice and one plug for data. We already do that now, voice over IP, and what we really do with voice over IP is the telephone is actually a little switch, 2-port switch, that you plug the phone into the network, and we'll talk about PoE, power over Ethernet, in a little bit, and then you plug the computer into the phone, and they both get access to the system through the switch in the telephone itself. But anyhow, back to this thing. When we make a start out of this, I didn't ever finish this up here. Let's go back to how we troubleshoot this thing. What I would do is we're looking for a low resistance when we connect an ohm meter through this wire. This is troubleshooting these things as wire, yeah. Wire. If we get like infinites, take a piece, you got to have a roll of wire to do this. You take a roll of wire, piece of wire, and you run it to the middle. And you connect it in the middle, and then you check the resistance to see which one is broken. If I get a 0 here, probably about 2 ohms, and an infinite here, then I'm going to put this one back together and take this device and go to the middle here to see where the break is. And that way I can get down to a very small area where the break is. In this thing, you would do the same thing. We'd go, and this one doesn't have a whole lot, but here we would have a T. What we would do is go in here and put a terminator on each end and see which half of the bus worked. That half's okay, the half that worked. Then we would go to the middle of what's left, do the same thing until you work. You can actually work your way down to a single workstation on those. But on this thing, everything, if I put a signal here, which computers see the signal?
All of them.
All of them. Which ones receive the signal? We're going to get to layer 2 stuff now.
Well, only the one, it depends on where you're supposed to be sending.
Which one's going to actually accept the signal?
They all receive it, but one takes it in.
Whichever one you let.
Whichever one what?
That you let.
That you
Receive the signal.
that you do what with? That I let?
Yeah.
How do I let it? You're right. How do I let it?
Well, it's like you talked about earlier about the whole addressing.
The whole addressing. And what kind of addressing do we have at the layer we're talking about here?
Is it MAC address?
physical MAC address. And when we looked at, that's an E.
That's pretty good.
It's a Euro, but no, it's a MAC. But well, we had two types of addresses, right? The logical address, the IP address, and a MAC address, built-in address, physical address, a lot of different terms, 48-bit hexadecimal address. You can see it on your machine, ipconfig, / I'll tell you what it is. Yes, you can spoof them. I'll show you how to do that later on. But, yeah, there's software to do it. You don't have to go to the software. All you got to do is go into the properties of the NIC and tell it to use this other address. But, yeah, well, that's one of the ways that you get into wireless, because what you hear is, hey, put MAC filtering on your wireless, right? Folks, hey, just go listen, protocol analyzer, sniffer, find a MAC address that's valid, put it on your NIC, you're in.
I really think that will stop like 90%.
Yeah, and WEP will stop 90% of the people.
Yeah.
WEP, if you really look at the definition, is, and what we would say for the casual observer, it's not designed to stop a dedicated hacker. But the MAC address goes on these things, and each of these has a MAC address, and we'll use really big ones, just like last time. Keeping in mind they're 48-bit. The first half is the manufacturer, the second half is actually serial. If we set this thing from one IP address to another, we would use the ARP protocol to eventually find the MAC address, and we'll look at the header as we go through these things, but we're going to have an IP address, an IP header, and a MAC header, and we got to get the MAC address. So if this is going to C, it goes out here and it goes on to the wire going to C, MAC C. This guy says, oh, there's traffic out there. Oh, that's not for me. So it moves on down. But we say that and I want to jump back to security. If we do this and the physical device that's going to do this is going to be a hub. If we do this, then we can see all the traffic, because we have to put our NIC into something called promiscuous mode. Not that way by default. I knew you'd like that. Promiscuous mode, which means that it sees all the traffic. It's all available. It's all available, right? It's all available, but it's not there until you shift the NIC into that mode. In the wireless, you can't do that with a Windows machine. You can do it with a Linux machine. You can on a wired network. You can put all of them into promiscuous mode where you see all the traffic. When we talk about switches, it doesn't do us a whole lot of good to do that. But now then that we've done that, we built this thing, and we have this logical topology at layer 2. That's a bus. Spent a lot of time on this slide, huh? If we wanted to make it a star, what we would do is put a box around this thing and shrink it, and we get one of these little devices called a hub or a switch. Let's say a hub, because a hub really is a bus device. A switch kind of is and kind of isn't. Token ring, and we talked about this, we go around these things, we have these things connected in here. The data flow, I have another card here, yeah. The data flow will go from one to the other, and it will get, the data, the ones and the zeros, will get renewed at each of these NICs. Token ring got a lot of advantages. Token ring got a lot of painful stuff too.
Those are the NICs with the two coax ports in the back?
Yes.
Okay.
Yes. How do we make this into a star?
What's up in the middle?
Same thing. You don't put anything in the middle. Put a box around it, shrink it. And he said you got an in and an out. So what we do is go, and these are called MAUs when we put them in a box, is an MAU, a multi-access unit. So we have an in and an out for each of these things that goes through. And we'll talk about how we get onto these things. So we have the logical topology, how the electrons flow, the bus or the star, and we have the physical topology. Can we have a physical ring? Sure. Can we have a physical bus? Sure. Physical bus going to be coax with T's in it. We looked at that a little bit. They do have some pictures of that here in just a minute. Does that make sense? The physical topologies, the logical topologies, and the data flow. Remember, we're talking about ones and zeros here, so when we get ready to regenerate it at layer 1 with a repeater, we can clean the signal up and actually create a new signal. The difference between, and I know that everybody was here last time we talked about this, between an amplifier and a repeater is an amplifier amplifies everything, including noise. A repeater renews the signal, starts it over. So let's see if we can get away from slide 4. Now I got to figure out how to get back into mouse mode. May create hybrid topologies. Hybrid topologies, we're going to mix these things together a little bit. Integral part of the network, cabling, infrastructure, transmission media used. This can be important on how data gets transmitted in your network, because when we go through these things, the devices that we talk about, each of the devices is going to have some delay in it. How far are we going to go with anything? How are we going to connect these things together? What kind of devices are you going to use? And hopefully when we get through with these things, what kind of devices will make some sense. Bus, single cable connects. We've already done all this, right? Single cable connects all of the devices together. Share the responsibility for getting data from one point to another. The one thing that we didn't talk about in the bus is how you get on it. You're sitting there, you're connected to it. How do you get to use it? How do you get to use it? More letters. You probably want to put them in your head this time. The way we get on a bus is a process, CSMA CD. What does that mean? When we talked about layer 1, we talked about carrier frequencies a little bit, right? The center frequency that we have. We had to have a carrier frequency before we can put any data on it, any intelligence on it. Radio station, television station has a carrier frequency that they do modulation with, amplitude modulation, frequency modulation, in order to put the news, the music, the whatever else on it. These things have a carrier too. The CS is carrier sense. Is there a carrier signal? Since we had all of these different devices connected here, we have multiple access. Carrier sense, multiple access. Is there a carrier? Sense the carrier signal. Multiple access. And then if I send my, use a different color here again, signal out here, I listen and I don't hear anything. I can go, right? Well, what if I listen and this guy listens and we both send our data at the same time? What's going to happen? Cancels out. We're going to have what's called a collision. And the collision detection. The collision is going to destroy the data packet. So collision detection, after we send the information, we actually listen for, and everybody should be listening for, a collision. If there is a collision, then what's called a jam signal gets sent out, which says basically the data got destroyed. When these get sent off the NIC, the way they do this thing, you actually make a copy of the data you sent so that you can get it off of the wire and then compare the two to see if anything has actually been destroyed. So carrier sense multiple access collision detection is what we use in a bus. Pretty straightforward, right? Terminator, stop the signals after reaching the end of the wire, prevent signal bounce. Terminator is simply a resistor that goes at each end of and it's really obvious on the coax, on the true bus itself, because it's an actual physical resistor that goes there that absorbs the signal. If we didn't do that, then you can get corruption because you can't resist this thing, can I? If we had this and we said we didn't have a terminator here, the way electrical properties work, we got this signal going out here, gets to the end, it'll bounce back. So you can get the signal bouncing back and forth. It won't ever go away. Layer 2 has some real issues with signals bouncing. If you don't do something with them, there's no mechanism at layer 2 to make the signal go away. When we get to layer 3, we're going to have this thing called time to live, which says, hey, you got so much time at this layer to live, which actually is the number of routers that you go through.
You talk about the sessions?
Just time to live, how many routers you actually go through. No, you're way high. You're up at the session layer. I'm down a little bit lower. What happens if we get things going around and around in a circle at layer 2? What makes them stop? Nothing. So how do we do that? We have to take account for it. On this thing in the bus, we actually put a terminator to absorb the signal. There are electrical ways and physical ways to make these things multiply as we do these things. But there is no mechanism at layer 2 to stop the signal from going and going and going. So we have to have the terminators, the signal bounce, the terminators stop these things from continuously going. Inexpensive, not very scalable, the bus itself. Are you going to actually see a bus? I seriously doubt it. Unless we build one for you, and maybe we'll build one later in this class just so you can see what it is. Actually, we couldn't do that because we don't have any NICs. We don't have any NICs that have T's, or certainly not in the machines, to create the bus. Could we create a bus through a hub? Yep. And I think we've got an exercise to do that so that you see the difference between a hub and a switch. What happens with these things. Are you going to use hubs? I hope not, although I guess some people are still using them. There are times when you want to use a hub. As a network administrator, when would you want to use a hub? When you want to see all the traffic. The switch isn't going to allow that unless we take some other actions to do that. And there are times that you would want to do that. Not very scalable because you got to actually run these things. And honest to goodness, the cheapest way that I know to put a network together now is with twisted pair. Switches are not outrageously expensive. You can get really expensive switches. You can get really inexpensive switches. The ones around here are a couple $300 a piece, something like that.
I saw one at Drill. It was just a little box with four, just like a tiny little.
Yeah.
Yeah.
Yeah, and those are like $12, $15. You can even get a gigabit for about $15. The full port, just switch, not a wireless, just the switch itself you're talking about, right? Difficult to troubleshoot, not fault tolerant. The bus itself, we talked about the troubleshooting. Any time there is a break in that bus, the whole thing quits. So, physical break in it. And here's their nice picture, which is a good picture of the terminator. I don't know why they've got this terminator going back to this computer here, because it's looking for the ground. The terminator is simply a resistor that absorbs the excess signal. Really fancy term. All it is a resistor to absorb the stuff. Let's take a break and then we'll do the ring smoker. Talk about ring here a few minutes. Ring is a little bit different than bus. The way you're going to get access to the media is called token passing, hence the name token ring. And what the token is an electronic signal that allows you access to the media. So the ring goes around in a circle, everything's connected to it, much better drawing than I made, obviously, but one to the other. It goes through these things, it goes through the NIC each time it goes around one of these devices. The star, see how I shouldn't have used it that way, should I? The ring, as it goes through the devices, the reason it did that is because I've still got a mouse mode. So when we go from one to the other, it actually goes into the NIC. And if it's to that device, again, it'll accept the information. Otherwise, it just does. And these do the regeneration through each NIC, so the signal's going to be clearer. And it's going to come back out and keep going. Kind of the same way until it gets to the location that it's going to. The token itself is just simply a signal that goes around, and when you get the token, you can put information on, new information on the media. So token passing, token ring, token passing is the media access control in bus, CSMA CD. In wireless, I guess I might as well throw that in, CSMA CA, collision avoidance in wireless. In wireless, you have to actually get permission before you send from the central location before you send the information. Star, we already talked about, they use hubs. You can see hubs? Maybe. Hub and switches, if you look at them physically, they don't appear to be a whole lot different, honestly. The one thing that you will see on a hub, but they don't show here, that you won't see on a switch is a collision light. So that you can get an idea, a visual representation of how many collisions that you're having. We talked about wire, and I guess we might as well cover this one. Wire. You did a straight through and a crossover, right? You will do a straight through and a crossover. Why? To learn how to make them. When do we use them each? Where do you use a straight through?
Straight through is for different devices.
Different devices.
Yeah.
What would be like a different device?
Like a hub and a switch.
Hub and a switch would not be different devices.
Oh.
I'm glad you said that, because that's what a lot of people think.
Like a computer.
A computer, like right here, this would be a straight through cable, unlike devices. And the one that is always my favorite, there's not a router in here. People connect a computer to a router, a NIC on the router. Say, oh, it's a straight through. No, it's a crossover. Like to like is a crossover. Hubs and switches, we'll put my unfancy device in here. Are like devices. So if you go from a hub to a switch, switch to a switch, hub to a hub, you're going to use a crossover cable. Sometimes they have what's called an upload port. If you look at those hubs back there, they actually have a switch, what I call a switchable port. I think it's port 24 has a little switch on it. You can physically switch it from a straight through to crossover, so that you can use a straight through cable and put it in crossover mode. The ones that we buy now are really much, much smarter, called auto detect. And it says, oh, I need a crossover? Let me fix this internally. Oh, I need a straight through? Let me fix this internally. So probably the switch that you have at home on your wireless access point is going to be an automatic auto switchable. The devices, the Cisco devices, are probably not going to be, and one of the reasons is just something else to break. And I guess they figured that if you're going to pay that much money for something, you should know what you're doing with it. Yeah, I know. I have two. And you plug in and say, oh, it worked. But I think that most of them, you have to look at the specifics of the device, obviously, but most of them are now auto-detect. So the straight-through, unlike devices, crossover-like devices. What these things actually are both what's called channel, instead of, because I think you looked at that, was 7-part data circuit. The channel device is what's here. That's why we don't have to have the two different types of devices to do the transfer here. So, like to like, crossover, easy to remember. The problem is, what are like devices, what are unlike devices? You got to look at things like NIC to NIC. And to me, these things, like, same kind of box to same kind of box. Once we get into serial, you don't have to worry, different cabling, different specifications, different little bit of everything. So these Ethernet areas, we do those things. Any single cable connects only two devices. The cabling problems affect the two nodes at the most. Kind of. We had an instructor here one time at nights, was teaching a class in room 101, I think. And the rooms that we're in, these are actually, even though there's a single piece of carpet here, these are actually false deck plates. So what we would do, because we didn't have these really cool racks that we've got in the room now, is you would take them, we were using hubs at the time, put the hub under the deck plate and have everything plugged in. He came in one morning and said, "Hey, nothing worked in that room last night. Nothing could talk to nothing." Well, golly, what would be your conclusion there if you're using a hub and nothing could talk to nothing? Hub's down, something wrong with the hub, and the hub was down, it was turned off. That goes back to the very basics, it's power applied. Those things happen. People trip over them, whatever else. Somebody had to make a real effort to get that one out, because you had to reach down under the floor, under the deck plate in order to turn it on and off.
Well, actually, Joseph, we was looking at the text service, some kind of things people say and everything.
Oh, yeah.
And, like, Joseph can tell stories better than I can. Can you tell a story, Joseph?
They called in and their computer wasn't working, and he was trying to help troubleshoot it, and he's like, "Well, where's the wires going to?
Yeah.
The back, is it plugged in?" All
Yeah.
that stuff. And he's like, "Yeah, it's plugged in." And he said, "Well, where's the second wire going?" And he couldn't tell. He's like, "Well, it's dark." And he's like, "Well, can you turn a light on?" And then he's like, "No, there's a power failure."
Yeah. Power's been out for about 2 hours. And the rest of that story is, you still got the boxes for the computer?
Yeah.
Yeah. Yeah. Yeah. So something wrong with it, right? So put it in a box, send it back. You're too stupid on a computer.
Yeah.
I confess to punch yourself in the face right now.
Yeah. And the people that the cup holder wasn't working?
Had that one.
Yep. How about the foot pedal? Foot pedal of the mouse.
Put it on the floor.
So, yeah. I can't imagine working in some of these help desks. Oh, I know. I can't imagine working in some of these things. But anyhow, theoretically, and honestly, troubleshooting these things, it's a central device. Either if they all don't work, then it's a central device. If one of them doesn't work, then it's just that device. And then you can go back to what is or what isn't, what layers it at, what's causing the issue to troubleshoot this. And if we go to a hub or a switch, how far do we have to go? What layer?
I'm sorry, what was the question?
If we're troubleshooting a hub or a switch, how far up the OSI model do we have to go?
A hub.
Hub would be?
Physical? Hub's on the first.
Hub's on the first.
Yeah, application.
Application 7.
Yeah.
Physical. Only physical, because a hub is a true bus. Could be power bug. What if it's a switch? It goes all the way to layer 2.
But a router is on layer 4?
Layer 3.
3, okay. I had them offset by one.
Yeah. So, what's causing these things? And honest to goodness, wire. Check the wire first.
Wire, dude.
Well, what happens how big do you think we talked about the voltages? How big do you think these voltages really are?
Not too big.
Not too big. You ever see anything that stayed plugged in a long time get corroded?
Yeah.
Doesn't take a whole lot to reduce the voltage going into that wire. Sometimes just unplugging it and plugging it back in will fix it. You don't get thermal creep anymore. Some of the old machines, you get this thing called thermal creep. Is you turn them on, turn it because they got so hot. You turn them on, turn them off. The circuit boards are working their way out of the sockets.
Oh, wow.
So a lot of times, and sometimes even a circuit card, take it out, and put it back in because they get a little bit of corrosion too, occasionally, particularly if you're in a humid environment. So those kinds of things. Cabling problems affect 2 nodes at most. Unfortunately, those 2 nodes could be 2 switches, so it could affect a lot of different workstations. You just have to look at the topology and how's it set up. Requires more cabling than a ring or a bus networks, more fault tolerant, the star. And you can see that in here. The switches are in the back of the room, so what do you got to do to get there? You run a wire from each computer to the punch-down block, and then you have a jumper cable that goes from the punch-down block to the switch. So you have to, instead of running, and if we just had a bus, we'd just run a piece of coax along each of the rows and plug the computers into them. Fault tolerant, if I unplug or if I break a connection going to it, it only affects that one machine. In the bus, if I broke the connection, it puts everything down. So when we do these things with more cabling than a ring or bus networks, it is much more fault tolerant. And honestly, has anybody seen lately anything other than a star in a work environment? Because wire's not all that expensive. Easily moved, isolated, interconnected with other networks, so it is scalable. If we needed to add 20 more machines in here, we could just put another switch in, can't we? And run the wires back to that switch, connect the 2 switches together. Is it going to be the best arrangement? It's going to be okay. It supports a maximum of 1,024 addressable nodes on a logical network. And these things are going to, these numbers are going to be a function of the switches that you're using. But 1,024, that's a lot. Probably not going to get there. Hub, oh excuse me, this says a hub. This should say MAU, a star wired ring. Slow down. Instead of hub here, when you see hub, think Ethernet. When you see if I can actually make this thing work. MAU, multi-access unit, think token ring. And what this shows is we go in and out. We have an in and an out on each port, the 2 wires we're talking about. As it goes down, it goes through the NIC each time, and regeneration, all those other things. The signal is going to be cleaner, but what's the issue going to be here, do you think? How long you got to wait to get access to the media? How long you got to wait to get access to the media here on the Ethernet? You don't have to. Just depends on how much traffic's there, right?
But isn't the Ethernet usually faster?
Up to about 80%. Up to about 80% network load. Once you get over 80% network load on a true bus, which we don't use because we use switches, and we'll get into those when we talk about switches, how that works. Yes. But if you're flying on an airplane, and I do that because that can be pretty dangerous if something goes wrong on an airplane, right? You want to use a token ring or a bus? Really?
No, a ring.
A ring because you're guaranteed access. Now, it may not be as fast, but you're guaranteed access. A bus, and they weren't here. I'll go through my story again. No right on red. If you're going to leave here, you don't want to stop at the light out there by, that's K&W down there, right?
Mm-hmm.
How you going to go? Take it right there at Lowe's and go out that back. You're going to go right on Hirschberger. You can go out by Lowe's, right? 2 o'clock in the morning, probably no problem.
No problem at all.
What about 5 o'clock in the afternoon?
Bad problem.
Bad problem. Probabilistic network. Ethernet is probabilistic, and this is my saying, not theirs. You're probably going to get on. What you got to do? CSMA CD. Carrier sense? Yep. Got the carrier. Multiple access. Getting on at the stop sign. Same thing, right? What you got to do? You got to wait until there's no traffic or until there's a break in the traffic. Deterministic. If you go out to the stoplight, eventually it's going to turn green. Eventually you'll get out. So that would be the deterministic type network access. And those are the two in the bounded media. Notice how I keep trying to bring these terms back in. Bounded media being that we use wire. Unbounded is wireless. If you see those terms, or you probably will at some point in time see those terms. So multi-access point, we've got an in and an out of each of these things. And you notice that as we go around this thing, that we actually have our ring, we shrunk it and put it in a box. So you actually have the ring in here. Most, and I go as far as to say, all of what you see today are going to be in some sort of a central device, a star of some sort. Even token ring, multi-access unit, a MAO, hub, switch.
If the wireless router was there instead of the hub, would it still be a star?
I'm going to say yes, although you don't really define wireless that way.
Okay.
And we use a different media access. We use collision avoidance for the media access. What actually happens, is it a star? Yeah, because it's a central unit that controls what goes on. When you want to use, when Nolan here is getting on and wants to send some traffic on his laptop that he's using on the wireless access point, he sends a signal to the wireless access point called a RTS, request to send. It says, hey, I'd like to send some traffic. If nobody else is using it, the wireless access point sends him back a CTS, a clear to send signal, and then he can send his data. And we'll jump ahead to acknowledgement. Every packet that you send to a wireless access point has to be acknowledged. That's one of the reasons they're slow. One of the things that makes the end more better, faster, is that you can actually group packets together, which you can never do before. When you talked about at layer 4 last week, talked about window size. How much can you send at once? So that you kind of have created that situation there. Star wired bus, and this is just terminology. Star wired, you connect two of these devices together. And hub, in today's networks, when you see hub, think switch. You're going to do the same thing. It's going to be called the same things. Serial network, serial backbone, daisy chain linked in a series of devices. And somebody asks, is this a daisy chain? And daisy chains are different things. But daisy chains are usually going to be device to device to device to device, same device type. Often connect in a daisy chains to extend the network. We can do that. It's not the ideal situation. The reason I say that is because we would like a higher speed, a backbone type speed, to go from the rooms here to the central distribution point in the NOC. And what we essentially have, and I think I got a picture here in a minute, is what they call a collapsed backbone. Because we kind of have a backbone, it's so small that we don't have to have a lot of device-to-device type arrangement. I don't know if it still is. When he originally put the two switches in this room, the one on the left side of the room actually went to the one on the right side of the room. And then that traffic went out from here. So he extended the network, and I think that now, because they had a limited number of ports on we go from here to a layer 3 switch, and we'll talk about those devices later on, just so you know what it is. Hubs, gateways, router switches, and bridges can form part of the backbone. Any of these things can be part of the backbone. The extent to which the hubs can be connected is limited. Hubs, yes. Because we have this rule for Ethernet called the 5-4-3 rule, which says that we can have 5 network segments separated by 4 repeaters, three of which may be populated. What we really have done here by doing that, and I don't think we really talked about how far these things can go, but Ethernet twisted pair could go 100 meters between devices. So what we've really done here is said that we can have a 500-meter network segment. The reason is, remember when we had this bus and we sent our data out here, what were we listening for? Collision. The issue becomes being able to actually detect a collision at the far end of the cable. Hence, it's a timing issue, is the reason that we have this 500-meter limit. Now, this is Ethernet. Go too fast with this, don't I? Ethernet is what topology? Bus. Can be a star. Remember, star is just physical. An Ethernet and a token ring can each be a physical star, but we're a logical bus. In a bus, everything sees everything. The reason I'm trying to make a point of that is when we talk about switches, we think of switches and we say Ethernet, but switches really aren't Ethernet. It's a switched network. We'll talk about those when we talk about the devices themselves and why they're different. But this, when we're talking about this, is Ethernet, is a true bus. We're talking hubs here when we do these things. And the 5-4-3 rule is an Ethernet rule, not a switched Ethernet rule. Well, that didn't work so good. The extent is limited. Router, switch, hubs. We got 1, 2, 3. And this is kind of a deceptive here because each of and they put switches in, backbone network, serial backbones. The switches here will be part of the backbone. Switches are going to be full duplex, and Ethernet's going to be when we have to CSMA-CD, and hubs are going to be half duplex. So that's the reason we're going to have collisions. Switches can't have collisions because they're full duplex. We have a transmit and a receive, and that's what your wires were. That's the crossover. When you did the crossover, what did you do? You crossed the transmit and the receive portions of the wire itself that went to the node.
You have to see the switches.
What if I wanted to go farther?
Okay.
What if or this one's just showing a backbone sort of arrangement. I think on this, you kind of jump from, we're talking about a 543 rule, and they put a switch in. Switch doesn't have to have a 543 rule. Why? We have to listen for collisions. Because what happens is the two ports that are conversing get connected together, and they are full duplex. So you can only send the data, you can send the data. What does full duplex mean? We can transmit and receive at the same time. We have separate transmit, let's do different colors here, and receive line. So we get down here to the hub, and now we put it all on the same piece of wiring. We get a half duplex device.
Because it's a ring inside there.
Because it's a bus. A bus, yeah, exactly, a bus. But you're thinking the right way.
So
It's a bus inside the hub.
in a sense, are you using the switch as a repeater?
Yeah, all of these active devices are repeaters. Yes, essentially that's what you're doing, is extending the range of the network. But when we talk about switches, do we have a 543 limitation? No, because we can't have a collision. Why did we have the 543 limitation? Because we had to be able to detect the collision at the far end. When we talk about that, the types of wires, and when you take the network plus, if it's twisted pair, pick 100 meters. The other one is 10 base 2. And I don't remember when we do these, but I might as well do these. When we talk about wires, you're going to see things like 10 base 2, and I'm going to write that again, 10 base T, 100 base T. I can do the base real quick like that, right? What this means is this is the speed. 10 megabits per second, 100 megabits per second, 1,000 base T, gigabit per second. The number over here, the 2, it's going to be coax, is 185 meters. The only other one you'll see like this is 5, and it's 500 meters. Which means that if we use this stuff, if we use the 500 meter using the 543 rule, we can go, what, kilometer, 2.5 kilometers. Using, and it's called thick net. It's like a frozen hose is what they call it, because it's thick and it's unwieldy and all sorts of things. Thin net is 185 meters, so you can go 5 times that, which is a long distance. The T's are, when you see a T, think 100 meters between devices.
That's twisted pair and whole twisted pair of that.
Twisted pair, T is twisted pair. Yeah. And you got TX, and the fiber's going to be a whole different world. How far you can go in fiber, depending on the type of fiber. Whether it's glass fiber, plastic fiber, on and on and on and on. But when you see these things, 10 base, the base, we're going to have a base or broad. And we talked about base and broad, I think, in layer 1. Base is baseband, 1 frequency. Broad is broadband cable. So base means that it is a base band single frequency carrier when we do these things. Broadband cable. We're not going to have a lot of broadband. The stuff that we're going to do, the Ethernet's going to be baseband single frequency, single carrier frequency. So you'll see things like 10 base, 100 base, 1,000 base. Speed, baseband, broadband is all that you can actually have there. And then the distance, how far you can go in a single segment. All sorts of stuff that you never wanted to know, right? Or maybe I already knew, I don't know. Distributed backbone, and these are all just different terminology, how we hook the stuff up. Distributed backbone. Distributed backbone, we have router. So the router connects these things together. And then we connect these to a switch, and the switch to the devices, and this one we extend the switch to a hub. Lord knows why you would want to do that. Well, I do know why you want. What if I want to see everything? Hub. Where would I put my hub? Going out here to the cloud. What if I want to see all the traffic going out of my network? What kind of device? There are ways to configure switches that we'll talk about later in order to do that also. It's called a span port.
Would you put a hub in between a router and a modem?
Between a router and a modem? Nah. You talking about at home?
At home?
You could. You could. Well, that's really what we're talking about here, isn't it? Because at this point here, whatever our ISP is, however we're getting to our ISP, it's going to be a router of some sort at this point. Because that's the only way you're going to get anyplace else. Yeah, you could do that in order to see all the traffic. There are other ways to configure switches to do that.
The router, you can't see, you're saying the hub will show you
all the traffic.
The router won't do that?
How are you going to monitor the router? It's got to be plugged into something, right? Ethernet port's got to be plugged into something. If I plug it into a switch, I only see the traffic to it and the broadcast traffic.
So if it's connected to a computer.
Huh?
Connected to a computer to monitor the router. Or I know,
How am I going to do that? Talking about, I'm way back at layer 1 now.
okay.
How are you going to physically connect it?
Well, the router in the top left corner.
And what we're going to do with it? Let's do this and let's hook it up the way you want it.
Well, I was thinking if you need to monitor traffic, you can build computer towers that function as routers.
Okay.
Would that be a better way to?
No, because computers are not designed to be routers. Depends on how much traffic. If I've got a little bit of traffic, I can certainly use a computer for a router. What if I got a lot of traffic?
Depends on the OS that you put on it. You can get operating
Yeah, not really.
routers loaded off of NICs.
Oh, sure. It's called Linux.
Yeah.
Still not designed to be a router.
It won't function just as well.
It'll function, but not as well.
Okay.
Yeah. What I really want, you know what I really want? It's a layer 3 switch. Wow. We'll talk about those. Actually, what I want to do after, maybe because we already talked about the OS, I will go over and look at the arrangement in the knob. Not anything sophisticated, but kind of get an idea where these devices fit in. We have a layer 3 switch over there. A layer 3 switch is something that can be a switch or a router. It's really cool because you can have 24 router ports on it. Pretty good deal, huh? 24 gigabit router ports. And you know what the really cool thing is about it? A router knows about everything that's connected to it. You don't have to put any route tables in for those things. It can figure out what everything is in the building without doing anything else. But anyhow, distributed backbone, and the distributed is because we have the different devices distributed at different locations. Collapsed backbone. So I tell you, this is kind of what we have. Because we have, if we say switch, and maybe this is room 111, that's us, right? And this is a switch, and this is room 108 or room whatever else. Each of these, and this will be room 100, whatever, other room, and each of these are going to be on their own subnet. We go back to a central router, which you could have multiple NICs in, or we could have what's called sub-interfaces. We can use a single NIC and have different logical interfaces on it. Logical and electrical, right? So we could have multiple IP addresses on that same NIC. by using those sub-interface, or we can use a layer 3 switch. But what we're saying here in the collapsed backbone, everything goes back to a central. It's kind of like a star, isn't it? Actually, if we move this thing up here, it looked more, they're all star, but it looked, and that's what they always connect it, put it in the middle of the room. Yeah, right. Everybody puts their device in the middle of the room, right? It's a star. Oh, sure. Put it in the middle of your house too, right? Mine's in the absolute worst location in the whole house.
Where's that?
On the second floor in a closet. Still works.
The worst location anywhere in my house. When they built it, it was really expensive, so they used metal.
Oh,
We used,
metal's really a lot of fun.
bought a brand new router, and from the room that it's in down a hallway that's probably about 20 feet, you lose connectivity.
Can you connect router to router?
Yeah.
Yeah.
So wireless routers, no router?
Yeah.
Can you use crossover cable?
No, yeah, you can do it wirelessly is what you're talking about, right?
Yeah.
What actually the 802.11n typically does is called a dual band router. It has a 2.4 gigahertz and a 5 gigahertz.
Okay.
The router connection is probably going to be 5 gigahertz because it's going to be faster, and then you connect your workstations, your computers too, using 2.4.
You can do that before then.
Yeah, you can do it.
So I've only seen it with Linksys.
Yeah, you can do it.
Set up for it.
Yeah, you can do it. The best is, I think, still a piece of wire.
Oh yeah.
So, but yes, you can. Absolutely. All sorts of cool stuff, huh?
Yeah. Would that make your connectivity with your workstations faster?
No, it'd make them much slower.
Oh, that's what I thought.
Because what we got to do, we just said what we got to do for every packet.
Yeah.
Got to acknowledge it.
But then again, it would increase the chances of.
Got to acknowledge it. And then you sit it, you got to acknowledge it. So it's probably going to slow things down.
The whole thing with wireless, right?
Mm-hmm.
If it was a wire.
If it was wired, then you would actually be using the switch component. It shouldn't make any difference.
Okay.
For a small home network, I don't think it would be too terribly bad. If you're trying to.
No, actually, I turned the radio off. I'm just using the switch in the basement. I finally got tired of it, and I ran a Cat 5 from the second floor to the basement, where there's a couple of machines.
So how many users on there do you think it would start to slow down? Like
Each device is different. Most of them tell you not to have. I think 12 to 15 is the number that they want you to limit to in most cases, but it depends on the device itself. What's the best way to do a denial of service in a wireless? Watch a movie.
Wait, what did you say?
Watch a movie.
Yeah.
Because you got it. Until you give it up, you got it.
Or download it.
Downloading, yes, all of those things. So everything has, and I know I jump around, and I hope it is okay, because everything's got an upside and a downside. No perfect world. You've got to find what's right for the individual circumstance, and that's what talking about all this stuff is about, is what's right for an individual circumstance. And what's right today may not be right tomorrow, honestly.
So if you did, like, connect them wirelessly, as I said, it would increase chances of more, increase range, right?
Yeah.
But it would decrease the speed.
Yep.
Okay.
And that's generally, I think, what you're going to find is the case, is that the closer things are, the faster they'll go.
Yeah.
The farther they're apart. And the Internet's kind of that way. In the building here, from here to the NOC anyway, we got a gigabit, 1,000 megabits per second. Going out of the building onto the Internet, we have 10 megabits per second. We go a whole lot farther, but we can't go as fast. So yeah, I think generally that's what you're going to find. Router or switch, this is, let's say this is deceptive. This will look really cool, right? This will work, but there are other protocols involved. And what's going to happen here, what's going to happen here, is one of these ports has got to be turned off. Why? Otherwise, we set up what we would call a broadcast storm. Oh, how do I get there? I go out this port. And then you says, how do I get there? Well, I can go, you flood it. You flood these things initially. We'll talk about those things. But some's got to be off initially or they get really confused. The protocols are there that if something goes down to turn it on. It does checking.
Like, I play Xbox Live and stuff, and then people talk about IP flooding.
Yeah.
Kind of what
Yeah.
it is.
Yeah. Something like that. You get broadcasts, and we can set those up. You can see those. There are protocols that are designed to stop that. And that's all part of also how do you set your network up.
Is that the same as feedback?
No, what that was there was a broadcast norm, and the spanning tree protocol is the one that Cisco uses to stop it. And we used to have an instructor here who was a Cisco kind of guy. He set up a big network in Chicago. Brokerage firm, something or other, I don't know. But they decided that they didn't want spanning tree broadcast protocol. Didn't want to use the little bitty packets. Didn't take very much traffic at all. But they decided that they didn't want to do it. So several months they've been running fine. Their network went down. They called him, flew him up to Chicago. He walked into the knock and moved one wire and went home. Somebody had moved a wire to create a loop. And got his consulting fee. So,
How much was consultant?
I don't know. He never said.
It has to be decent to fly you up there.
Yeah. Logical topologies may not match the physical topology. Probably have said that enough. The logical topology, the bus logical topology from one device to the other, the logical bus, the physical star. The two logical topologies that we've talked about are bus and ring. Physical topology is, I'm going to give you the question for the right answer, star, right? And those are the things that we've talked about. Circular path, hopefully we've done that. Switching is a component of the network's logical topology. It determines how connections are created between nodes. Circuit switching is established between the network nodes before transmission. We create a circuit between these things. So the layer 4 is going to be called connection oriented. That's that synchronization, the acknowledge and another synchronization, and then the acknowledgement, so that we actually create kind of like a phone call. Before you start the conversation, hello, this is da-da-da. Remains available until the communication is terminated, and we'll get up to Tom's session layer, because that's what the session did, right? Terminates, establishes, and terminates. There's not a lot of different things that are happening here. Remains available while it's connected. All the data flows along the same path initially selected. What that says is that we determine the route that it's going to take before we start sending the data. So we establish a circuit. All of the switches, the phone switches get switched over, and that's how a phone call gets there, right? They just keep falling over until it actually gets switched over to your number to get from point A to point B. Can result in a waste of available resources. And the reason that's there, what if a faster path becomes available? Can you use it? Not in this, because it is switched. Message switching. A connection between two devices transfers the information, breaks the connection, finds it again. And what this is saying is they don't all have to go over the same path. We can have different paths. let me see if I can do this here and kind of make something that maybe makes a little sensor. Yeah, that's what I wanted. Let's say we'll just put a bunch of the circles are routers, okay? Bunch of routers out here. We can have multiple paths across these things. Let's have the red path. The red path. Maybe we can have a bunch of multiple paths. It doesn't like me today, does it? The blue path. May be better, right? May not be better. And how can we do these things? In the circuit switched, what we do before we start the conversation is we establish the path. All the traffic goes over that path. In the packet switched, the first packet might go this way. And again, that always looks good. That may or may not be the fastest path because of the transmission speed between these devices. Breaks the connection. The next one might go, I didn't have one, but we just made a new path, this way. The third one might go this way. So circuit switched or packet switched, depending on how the network is set up, obviously. But that's the difference between those two terminologies. Almost to get this thing figured out. Packet switching breaks the packet. Packets travel on any network path multiple directions. They don't always go the same path. It's kind of like when I was talking about the letters from the ship. Don't always go, and certainly don't always go the same direction. Efficient use of bandwidth, because this used to be called, I don't know what it is on the fly switching, because what it would do is find the most efficient path and would use that path. Will do is to do that. We don't have to do this because we already did this, right? CSMA-CD. Ethernet, NICs, listed on the network, da-da-da-da-da, you can read that. Have we beat that one to death? We haven't?
Yeah, we have.
Okay, we have. Jamming, the NIC indicates the network knows that the previous transmission was faulty. Jam signal says, hey, I got to redo this. When it gets a jam signal, the one thing I did forget to say, gets a jam signal, it goes into a random back-off. Random back-off. Why random back-off? Why don't you say back it off for 3 seconds? Then both of them transmit at the same time and bang. If you are on a ship in fog, you have fog signals, but you're supposed to give fog signals at random intervals. Because if you're giving a fog signal every minute or 3 minutes or 2 minutes, and the other guy's giving us a fog signal every 2 minutes or 3 minutes or whatever, you can't hear his. And then you have a collision. And then you'd be looking for a job. So, random back off so that you just don't do those collisions. And this is the same process. Listens for activity, detects activity, no, it transmits, detects a collision, no, the transmission complete. If it's yes, stops transmitting, jams, then waits, and then goes through the same process. If you detect activity, you wait. So, kind of the thing that we talked about. Switched Ethernet, fixed amount of shared Ethernet is a fixed amount of bandwidth shared by all devices on the segment, and all nodes in the segment belong to the same collision domain. And before we start talking about this, let's take a break again. Fixed amount of bandwidth, and there is a fixed amount of bandwidth and throughput. Think about that. Bandwidth, throughput, we talk about them in the same terms, and they're in a strict definition different, but shared by all devices in the segment. It's kind of like a highway. And Ethernet, honestly, think about like a highway, 2-lane highway with a 1-lane bridge. If you're by yourself, it's okay, right? But what about at 5 o'clock? Where you get all that congestion. And what happens? Collisions. And that happens anywhere, but you have a certain amount of bandwidth, a certain amount of highway space. Similar conceptually what goes on here. All nodes belong to the same collision domain. That's in a hub. And that goes back to again, I can't resist the pen here. We connect all these things together and we can have collisions. And that's a collision domain. That's a single collision domain. I'm probably going to jump ahead, but when we do a switch...
That reminds me of one row with multiple intersections.
Say that again?
One row with multiple intersections.
One row with multiple intersections. Yep. A lot of different stop signs that you got to check to be sure nobody's coming. Turn right or turn left, kind of deal. Slow down, speed up. And the more traffic there is, the slower you go. And if we have a collision, what happens? It just really backs up then, right? It was bad enough. Roanoke has got like no traffic. I was going home last Thursday night, and there was a car that apparently had broken down in a left turn lane.
I have one where
and it just backed up forever.
cars wrecked into each other, both people got out and ran.
Okay, they won't get out and run here. But what happens in a switch is we got dual paths. We have dual paths, interstate highway sort of arrangement. What happens in switching nodes, and in these, in the Ethernet, they all belong to the same collision domain. What I'm trying to do, and I don't know if I'll do a good job or make it a bigger mess, is to distinguish what happens in collision domains and switches. In a switch, if we have multiple machines connected to it, and again we'll have these big addresses A, B, and C. If A wants to go to C, it sends its traffic to the switch. Now, if we were here, and we had A, B, and C, we'll have them upside down, it'd go out, everything would be able to see the traffic, right? Mm-hmm. In this one, the first time that the traffic goes out, it's flooded, and flooded is the term that's used out of all the ports.
On the bus you drew,
Mm-hmm.
You left off D. Would D still be able to see the traffic?
Oh, yeah. I just didn't go that far.
So the signal bounces to the end of that, okay.
Yeah, and then we have the terminator here, which absorbs this excess signal. Okay? In a switch, let me try a different color here, see if I can get these things separate a little bit. The switch, first thing we go into the switch to send traffic, and we want to go from A to C. Well, these things create an address table of the MAC addresses.
I was wondering how they did that.
They create and you're going to see it, I'm going to call it MAC. In Cisco, they call it CAM. The first time I thought they spelled MAC backwards, but it didn't. It's content addressable memory. So you'll see it as both MAC and CAM. Okay? And it's not MAC spelled backwards. So it goes up here, and we'll say this is port 1, and this is port 2, and this is port 3. When the traffic comes in the table, it says port 1 has address A on it. Okay? When it gets here, it doesn't know where anything else is yet. So it floods the traffic out of all of the ports. Well, C says, hey, that's for me. So C goes back to enter the traffic, and now we know that on port 3 we have C. The next time that the traffic goes from A to C, since it has this table, it goes directly. The ports are switched together. Those are the only two that are conversing on that switched network, I guess is a way to say that. So it learns the switch learns where everything is, and then when the traffic comes out from A to C, it says, oh, I know where C is, it just sends it out that port. That's why whenever you put a protocol analyzer, nice name for sniffer, on this computer A here, all it sees is traffic to it. It doesn't see any traffic if we put another one out here. It doesn't see the B to D traffic because that's a dedicated connection. It only sees the traffic to it and broadcast traffic. Broadcast traffic is traffic that goes to everybody, so it goes out all the ports. Now, having said that, this here we see everything. How many collision domains do we have here? Bingo. Every port's a collision domain. Because it creates a connection to where it's going. So switches, collision domains, switches can't have collisions. Because it's also full duplex. No, I didn't draw that. So we got the transmits and the receives connected to each other. The interstate highway theoretical won't have collision sort of arrangement when we go through these things. So all nodes belong to the same collision domain in a hub in an Ethernet. In a switched Ethernet, in a switched environment, every port's on its own collision domain. And not only that, since we have two of these, and we got 100 going this way and 100 going this way, we just doubled our speed by being able to go at the full speed on both of those in each direction, because we can transmit and receive at the same time. Does that make sense? Kind of. What doesn't make sense?
It was got a lot of information.
I agree with that. Drink with a fire hose. Gets worse. We get a bigger fire hose for some of these classes. It is. It really is a drink with a fire hose. I agree. There is a lot of information. You get no argument from me about that. But if we don't do that, you have to pick what you don't want to know. So somebody said one time, too much information in this class. I said, okay, what would you like to not learn? Switch enables multiple nodes to simultaneously transmit and receive, and that's kind of what I was trying to go with. It increases the effective bandwidth of the network segment because we can transmit and receive at the same time. And the computer can handle that. The switch in the hubs, the switched Ethernet, and the reason they do collision domain. So in this one, still can't resist. These hubs, a collision domain here because a hub, they're all in the same collision domain. Collision domain here because they're all in the same. So in this one we have created 3 collision domains. If we took something out here, it would be in its own collision domain. We'd have 4. Anything else, so anything that comes out of a switch, every switch port, is its own collision domain. How does that help us? Can't have collisions. If you were on a street or a highway and couldn't have collisions, It'd be really good, right? Because you probably could get there in about the time that it says on your GPS. Last time I tried to go anywhere, I had a collision up around Winchester on 81. Took about 3 hours. Same thing happens here. Traffic, we're talking about traffic. Conceptually, not a lot of difference between highway traffic and network traffic in those sorts of arrangements. Ethernet frames, maybe I'm going to. Maybe I'm not going to. Just doesn't want to talk to me. Different frame types. There are a whole lot of different frame types. This used to be a much, much bigger deal when we had Novell. And on the Novell, actually on the Microsoft questions, they always had one that you can't get onto your NetWare server. What's the problem? The problem was always the wrong frame type. That was always the answer. What we're really talking about now are basically 802.3 frames. Huh?
What was the answer?
Wrong frame type, because we had a lot of different frame types. Not going to see that a whole lot anymore. We're going to talk about Ethernet frames. What's in the Ethernet frame? Frame is the PDU for the data link layer, right? Some people fight back. Did I say that, or I just said that? What they were? How do you remember the frame types on down? Some people fight back. Transport segment, people, network packet, data link, frame, physical layer, bits. Some people fight back. And if you want to put data in there, don't some people fight back. So, how do you remember the PDUs? Some people fight back. No relation to the network's topology or cabling characteristics. The frame is simply the information that goes in at layer 2. Cannot expect interoperability between frame types, and you may see that. Typically, you're not going to see a lot of frame differentiation in today's networking world. Used to, because we had more different operating systems that actually operated in the networking world. And NetWare and a lot of these presentations, and Microsoft still convinced through Server 2003 that NetWare was still viable, is not, because they had their own protocol to connect with a NetWare network. Through the device's configuration software automatically sense, and here's the key, most NICs automatically sense frame types running on the network and adjust, and that was the answer to this. To the Microsoft question, how do you fix it? Put an auto sense. Let it automatically sense these things. The Ethernet frames, and they got a picture here of a frame, a 7-byte preamble, starter frame delimiter, a 14-byte header, destination address, source address, MAC address, 14-byte header when we go through these things. Additional field that varies in function and size. A 4-byte frame check sequence, that's where we get the error checking, is a frame check sequence. And every layer can have some, not every layer, but a lot of the layers, as you notice, may have some error checking in them. Data portion, 46 to 1,500 bytes of information, 1,500 bytes of data per frame. When we put these things together, they're a little bit different. The Ethernet 2 DICs, preamble, destination, source. Notice we have the destination address first. Why do you think that is? Why would you do that? Because mostly you do the from to, right? And at layer 3, it's from to.
That way, right?
But yes, it does. In the upper layers, in the layer 3, the other address that we have, it's got the from to.
If you've ever talked like over CVs or walkies, you say who you're trying to
That's
call,
right. Yeah, I agree.
and then you say who you are.
There is a reason we have, and I'm going to talk about it here in a minute, but I'll cover it now. 3 types of switching. Because this is Layer 2, right? And what device operates at layer 2? Data link layer. What the device operates at data link layer? How about the switch?
Getting better with the thing, eh?
Slow it down, yeah. In the switching world, we have 3 types. And I don't know if I'll be able to get these up here. I'll do the abbreviations. One, store and forward. Gonna be slow, right? Because you get the whole packet before you can send it out. The other one is going to be called cut through. Cut through. What cut through says, as soon as I know where it's going, send it there. Doesn't do any checking. The third type is going to be called fragment free. Did I get that? Free. It reads a little bit more. It reads the first 64 bytes of data and then forwards it. So if we had these reversed, we'd slow down the cut-through switching. So the cut-through switching, as soon as it sees the destination address, it sends it there. It doesn't check anything. The store and forward can actually do the frame check sequence and those kinds of things, can check for corruption before it forwards it on. These others just send it. Fragment free, the first 64 bytes, checks the first 64 bytes because most collisions occur within the first 64 bytes of the frame. So those things. But destination address, exactly what you said. When you're talking to somebody, it's the called station goes first. Doesn't really work that way. It's the from to in the layer 3. But the reason that these are is so that you get that address. As soon as it reads the destination address, it sends it to that port or that device, if it is a device that is sending it to. Power over Ethernet, 802.3AF. Have you looked at any of the telephones around here, just out of curiosity? Any of the Cisco phones? Golly. You know what they don't have? Power cord. Why is that? 802.3AF says that we will send the power to the device via Ethernet. What do you think would happen if you plugged an unpowered device into a powered port? Burn it up? No, not really. That's what I wanted you to say. It goes through a checking process to see if it actually is a powered device before it just turns it into a regular port. But we have a power over Ethernet. One switch in the NOC is a power over Ethernet switch, and so we'll go back and look at some of those things after we do this. Power over Ethernet switch, which has all of the telephones plugged into it. That's kind of handy because you don't always have an outlet where you want a phone. Wireless access points, some of those will use power over Ethernet because sometimes you don't want them. You want them a lot of times where they put them in the ceiling. So people can't see them, but they're available. Better transmission. If you can power it without having to put a power plug there, it's a lot better, and that's what power over Ethernet does. The 802.3AF standard does that. Useful nodes, powered receptacles, away from receptacles, all of those sorts of things. Power sourcing equipment is the device that supplies power. When you get into this thing, if you don't have a power over Ethernet switch, you can get a device that you can put into your network that will provide power for it, that you can power your devices. They actually tend to be relatively expensive. Power devices receive the power from the power sourcing equipment. Cat5 or better copper cabling in order to do that because you've got to send the power that way also. Token ring, I think the only thing that we didn't really talk about in token ring is the speed, 416 at 100 megabits per second. For a long time, the high-speed token ring is 100 megabits per second. For a long time, it was only 416. And token ring only operates as fast as the slowest device.
That would be what?
Only as fast, if I had 300 megabit devices and a 4 megabit device, I just created a 4 megabit token ring. 4 megabit per second token ring. So it only operates as fast as the slowest device. The lowest common denominator, lowest common device. The token, we've talked about, that's a 3-byte packet transmitted between the nodes in a circular fashion in a ring, and the station has something to send, picks up the token, changes it to a frame, adds a header information, and puts it on the field. So you got what that's saying is you got to have the token in order to transmit information. Avoids collision, but we already figured out how to do that by using the switch network, right? It's going to be, generally, switch networks are much, much simpler to manage, because when you do this, if you put a device in the token, you got to add it to the ring, and how often does it get the token? There's a number of configurations that have to happen. The active monitor maintains the timing for the ring passing. Monitors these things, monitor to be sure that they've got connectivity. It's a self-monitoring device, and you wait so long before you don't get something from your nearest upstream neighbor or to your nearest upstream neighbor and report as a network failure. So it does some monitoring itself where Ethernet doesn't do that. The MAU, we've talked about self-sorting feature of the token ring. MAU ports make the token ring highly fault tolerant. The MAU in and out, and each of the devices have a ring in and a ring out port. It's kind of like an uplink port to connect or to connecting two devices together in Ethernet. Although you don't have to worry about the direction, which is ring in and which is ring out, because it's got to go in a single direction. FDDI uses a double ring, multi-mode fiber or single mode fiber, multi-mode or single mode, how many different frequencies, and that's going to affect the speed. Different light frequencies light frequencies are really modes. Mode is a path. So do we have multiple paths or single paths? And probably don't want to get into that. It's a fiber, first network technology to reach 100 megabits per second, so that tells you that it's a relatively old technology. Frequently found supporting backbones installed in the 80s and 90s, so it really was designed as a backbone. Used on MANs and WANs, can link distances up to 62 miles, so we're going to get some good distance with these things. Reliable, secure, and expensive. What it has is counter-rotating rings, and if you look at this thing, these arrows are going in each direction. So what we have here is it goes through each device twice, each node twice, and these are going to be like servers. That's what you're going to put on your backbone. So a primary ring and a secondary ring, so if there is a failure, then the other direction can pick up the load, and you don't lose your continuity. ATM's an ITU standard describing the data link layer. We really got a long way. We're already up to layer 2, and we're halfway through the course now, right? We're only going to go. We're not going to go with that. We're not going to go all the way to 7 in this part. Packets called to cell always have 48 bytes of data, and cert stuff that I've seen, what they want you to know, it's a constant size 48 byte cell for ATM. I said we use frame relay. Internally, frame relay actually uses ATM to send its data once you get into the frame network. Consider the packet switching. Packet switching, circuit switching were the two types of switching. So packet switching means that each one of them can go different paths. Guaranteed quality of service, guaranteed bandwidth is what we're talking about there. Specifying the data will be delivered within a certain amount of time. So those are there. LAN emulation allows integration with Ethernet and token ring network. So we have the flexibility to do those. 802.11. B, A, G, N, and now AC. And yes, they do share many characteristics, half duplex. One of the issues, not really a problem, but you can't really detect collisions. These things can't always necessarily detect each other. That's why we use a CSMA CA. If we have our wireless access point here and we have a laptop here and a laptop here and we're 100 meters and 100 meters, these two guys will never see each other, right? Theoretically, anyway. So they don't know they're there. So in these we use CSMA CA, collision avoidance. Whenever I want to send something, I go to the access point, and we said this earlier, send an RTS. Really messed that up, didn't I? And if nobody else is using it, it sends me back a CTS, a clear to send, and then I send my data. And it acknowledges receipt of my data. And then we're probably going to get onto a bounded, a wired network out of there, out of the switch portion of it. Typically, you're not going to want to stay on the wireless because they still tend to be slower than everything else. Half duplex signaling, everything has to be acknowledged and tend to be, compared to wired networking, slow. Access method, MAC services, the 48-bit, the same things, carry sense multiple access, collision avoidance to access these things, ACK package used to verify every transmission, what we said before. Every transmission has to be acknowledged. That's going to take some time. And until we got to the end standard, we couldn't group these transmissions together like you do with wired. When we do wired networking, when we talk about layer 4, we're going to create a window size. How much data can you take at once? How big a byte can you take? And they'll negotiate, figure out how much data. And when we acknowledge it, we acknowledge receipt of all of those packets, multiple packets in the same transmission. You can only do that in the end standards. You can't do it in the A, B, and G. The request to send, clear to send, enables the source node to issue a RTS signal to the access point, requests exclusive opportunity to transmit, because you have to have that. And again, that's not the case. You can have multiple paths in the end, multiple antennas. The reason is you have multiple antennas. You can have up to 6 antennas in an end network device. So you can have multiple paths, multiple transmissions at the same time, and you can group transmissions together. That's how it gets its speed. That's why it gets faster. Associations, the communication station and access point to connect to the network, scanning station surveys the access, and you've seen that. How many are available? You click on it, it's either secured or not secured. And if it's secured, you got to put in a key code of some sort, depending on which protocol you use as we go through those things. Active scanning finds the SSID. That's another thing they tell you to do, right? To keep your secure, turn off your SSID.
Yeah.
Turn off your SSID and do MAC filtering, and your wireless access point is now secure. True? No. The SSID goes in a lot of packets that you can receive using a Linux machine at layer 2. So you can get all that stuff. You don't have to have air snorts. You can do it with Wireshark.
Yeah.
All you got to do is enable monitor mode, promiscuous mode, in order to be able to see all the traffic. Bunch of access points to the wired LAN, and Joshua asked, can we connect these things wirelessly? Yes. Is it going to be slower? Yes. Because back to 3 slides ago, every wireless transmission has to be acknowledged. So that's going to slow things down with all those acknowledgments. Its frame is a little bit different because it can have multiple addresses, which kind of makes sense because you got the source destination address. You may have the address, probably going to have the address of the access point also. And so its frame, as you can see, a little bit different than the wired frame. So we have the frame control at the duration. How long do you think you're going to need to tie up the access point? So you get exclusive use of it for a certain amount of time. Address 1, address 2, address 3, the sequence control, and then we got just for added measure and another address back here, and then the data that goes in here, the frame check sequence. When you get to the remote, the send-it site goes through the same algorithm to see if we produce the same string of characters for the frame check sequence to see if the information was damaged en route. Bluetooth, you guys probably have used that. I know you've used that. Uses FHSS, frequency hopping spread spectrum, RF signal. The reason, I kind of point that out, that's what 802.11b used also, the original B. The G's don't use a different type of modulation. It's slow. And how far does Bluetooth go? Not very far. That's a good answer. Depends on which one, which standard. Let's say 30 meters, 35 meters, 30 feet, something like that. I've taken this thing that I use and record, and I've walked back to the faculty office and still be connected to this machine. So it depends on the environment that you're in. Wireless becomes really funny. We're almost done. I got one more story to tell you about wireless in the Persian Gulf. At sea, we would set up at Bahrain, and using our 30-mile surface search radar, we could watch traffic in the Strait of Hormuz, which is probably 300 or 400 miles away. Depends on the atmospherics. How far is it going to go? Depends. I mean, there's all sorts of things that go in there, but there aren't any guarantees on any of this stuff. PicoNets, nice term that they probably ask you. PicoNets, just very short distance. So we have LANs, MANs, WANs, and PicoNets now, right? When we talk about these things. IR. I think if I ask you, is anybody, I haven't seen it. Well, actually, yeah, IR, I've got one right here. And we all probably use an infrared transmitter, right? Your remote control for your television. Although some of those are actually now going to Bluetooth devices. Infrared, keyboards, receivers, mouse. The problem with wireless is, how far does it go? Not very far, but what is the problem? Who can see it? Anybody. What if we wanted a wireless solution that wouldn't go out of the room? Infrared's slow, doesn't go very far, but doesn't go through walls. Whereas wireless RF does. That's the only real reason I can think of that. I had a telephone one time that had connected to the computer. You could transfer information. Now you use Bluetooth or USB or whatever else to transfer stuff from the phone. This table's in the book. The standards and the speeds in IRDA is infrared. See, it's a real high speed. Bluetooth, real high speed too, right? 2.1. And then the effective throughput is the thing that you want to look at. And notice that the effective throughput runs, what, about half of the theoretical maximum throughput? Because this was a half duplex system, right? So you're going to get about, whatever they say the speed is, you're going to get about half in wireless. So I was never going to get here, didn't you? So what's the difference between a physical topology and a logical topology? Or do I have to start over? Actually, I'll just make you listen to the recording. What's the difference? What's a physical topology?
How it's physically set
How it's physically set up, what it looks like.
Yeah, wires plugged into the machine.
where the wire's plugged in.
The logical topology may be totally different.
May be totally different, absolutely. What were the two logical topologies that we talked about? Bus and ring. Bus and ring. And those can be physical or logical, and the other physical was a star. The star is only a physical topology. Bus and ring. Bus had collisions. Ring didn't have collisions. Switches don't have collisions. Hubs do have collisions. Hubs are layer 1 devices. Switches are layer 2 devices. Backbones, high-speed connection with a bunch of, then you can look at the pictures, the way that they do the backbones. Collapsed backbone goes to a central device, and that's really what we have here in this building. Ethernet, CSMA, CD, wireless with CSMA, A.
Carrier, you want to describe it?
Yeah.
Okay, carrier sense multiple access collision detection.
Detection, CSMA, CD, Ethernet. Token ring is token passing, and you'll see that as the media access control is token passing because you get the token. FDDI is an old standard counter-rotating ring is really what you're talking about there. ATM, 48-byte cells in here, and it's also what frame relay uses. And it's a packet switch network. Say again?
I was just repeating
ATM, yeah. Not the place you get money, but asynchronous transfer mode. Questions? Probably ready for me to quit, right? Are you asleep yet?